Um, yeah, so welcome to this course on Introduction to Statistical Learning Theory. This is a continuation of the concentration inequalities course. Is there anyone who has not taken the concentration inequalities course? Okay, I will expect that as a prerequisite. So either you will have to read up on that in parallel or something. So there are essentially some basic results from concentration inequalities that I'll keep using, particularly the Chernoff bounds and Hoeffding and Bernstein's inequality. The lecture videos for that course are also available online on my webpage. You can take a look. But I'll assume that you know that in this particular. Um, okay, so as I said, prerequisites is concentration inequalities. In any case, you should have done at least an undergraduate or a graduate course in probability random processes. That's a minimum requirement. You should know some programming in Python. We won't do too much programming. It's going to be a math heavy course. But we at least maybe a couple of programming assignments and some examples that I do in class may involve some programming. Right? And homeworks will be posted. I'll keep giving exercise problems in class, but there are only going to, but evaluation will essentially be based on 2 exams. It's a 1 credit course, so there will be a midterm exam roughly week of 25th September. We'll finalize the date maybe by next week or so. The final exam will be in class on 17th October. That's the last class of this particular segment. Okay. Is anyone planning to audit this course? Okay. Are you auditing it for an AU grade? Are you just sitting through the course, or are you attending the course because you want an AU grade? Do you want it to be reflected on your transcript? Okay. So basically, if you're formally auditing this course, then you have to write the exams and get a pass grade to secure an AU grade. That's the requirement. But of course, you're free to just sit through this course. No requirement of attending any exams. Okay. Yeah. So the time slot and class, everything is fixed. This is a course webpage. So anyway, I will be sharing the details. I'll add you all to the Google Classroom for this particular course, maybe by later today. If you have not registered for the course, don't plan to register for the course, then just send me an email. I'll add you to the Google Classroom. Okay. And all other material like class notes, references, and recordings of lectures will all be posted. Everything will be available on this course webpage. You can also get to this course webpage by just visiting my website, going to teaching, and you can get it here. I'll mainly be using these 2 references for this course. The first is a book called Understanding Machine Learning from Theory to Algorithms by Shai Shalev Schwartz and Shai Ben David. It's a very nice, gentle book. It does not assume a lot of prerequisites and is very easy to follow. In fact, there are even lecture videos by the authors available on YouTube. So that's also a great resource. The other is this book called Foundations of Machine Learning by Mori, Rostamede, and Talwalkar. This is also a great book, but slightly more advanced. It's a bit more rigorous and gets to things much faster than the first book. And I'll mostly be using these 2 books, but this is also a nice book which is perhaps even more slightly advanced. And again, as I said, we'll be using some basic results from concentration inequalities. We covered most of that in the concentration inequalities course, but maybe I didn't prove all of the results. For example, McDermott's inequality and things like that. And these are some references that you can go through. There's a lot that we did not cover in that particular course. And this particular paper, it's maybe 20-25 page paper. It covers the essentials of everything we are going to do in this course. So it's a great paper, so I would encourage you to read this. All right. Yeah, and there's a tentative list of topics and other material will be uploaded on this webpage. So any questions related to logistics? No questions? Okay. Quick show of hands. How many of you are from the AI department? Okay. EE? Other departments? Which department are you from? Yes. Okay.
Yes.
MNC. Good. How many of you are postgrad students? Yeah, another point is that this course is a prerequisite for EE 5605 kernel methods, which will be offered in the last 2 segments of this semester. So we will, in fact, be borrowing a lot of stuff from this course into that course. You can think of it as sort of just a continuation. I will not recap things when I start the kernel methods course. Okay. So how many of you have already taken a course on machine learning? Okay, which is a majority of the course. Some of you have not. I will not assume that you have taken a course in machine learning because we'll essentially be starting from first principles. All right. So again, getting down to the material itself, the goal is to essentially build up machine learning from first principles. Right? How do we, given an engineering problem, which is designing a learning algorithm, how do we formally or mathematically frame this particular problem in a way that we can quantify the performance of a particular algorithm? There are a number of different rules used in like typical machine learning problems, like algorithms, certain sub algorithms that are used in machine learning, which arise out of these principles that we will build. Okay. So zooming out, what is the goal? The goal is to design a machine learning problem. And what exactly does that constitute? The kind of problems that we want to solve are, so you can think of them in the following ways. So for example, you may want to solve text or document or image or video classification problem. So for example, suppose someone gives you a piece of text, maybe an email, you want to classify it as whether it's a spam or not. Or if you, let's say, are given a document or maybe a book, maybe you want to categorize it into different topics. For example, is this a math book? Is this literature? Is it philosophy? Something else. Or if you're given an image, you may want to say whether this image has a car or not, whether it has a person or not. Or if it has, let's say, handwritten digits, you want to find out what digit is present in that particular image. Or if it's something like audio or video, you may want to classify it as, okay, maybe you want to classify different kinds of music in the audio, right? Or, and so on and so forth. So that's one sort of broad class of problems which are similar in some sense. It could also be some kind of a natural language processing problem. For example, maybe you're given either text or audio of maybe speech, right? And you want to, there are different kinds of questions that you can ask. Can you identify who the speaker is? Or maybe in the context of natural language processing, maybe you want to find out the parts of speech, right? Whether you have a sentence and you want to say whether this word is an article, this word is a noun, it's a pronoun or a verb, and so on. Or you may want to do, let's say, next word prediction. Someone gives you a part of a sentence and the goal is to complete that sentence. Or you may want to say translate text or audio from one language to another. All of these are, broadly speaking, language processing problems where there is some inherent structure. I mean, all of these have some kind of structure, but you also know something about this specific structure of the text or audio that is present. Similarly, speech processing, wherein you're given maybe a clip of audio, you want to identify who the speaker is, or yeah, again, so in many of these problems, there's not a clear demarcation whether you want to classify a specific problem as a natural language processing problem or a speech processing problem. It's a little bit fuzzy, but sometimes you can clearly distinguish whether it belongs to this class or this class. Similarly, computer vision, maybe you're given a video clip and you want to find out exactly where there are humans present. Or you may be given an image, maybe an aerial image, and you want to demarcate which regions correspond to buildings, which regions correspond to, let's say, vehicles, and which of it corresponds to fields, and so on. Right. And or you may just want to count the number of people or number of objects of a certain type in an image or a video. Right. Or you want to track something. Let's say you have a video, there's an object that is moving around, maybe a ball that is bouncing around, and you want to track the movement of this particular ball. All right. So you may want to solve problems in computational biology. So for example, will a certain drug help you fight a certain disease? Or how do you find out which, let's say, parts of the DNA contribute to specific traits of an individual? Or what kind of drugs can help you fight certain viruses? Or how are certain proteins synthesized? How do proteins fold? What is the 3D structure of a particular protein? All of these are computational biology questions. You may even want to, let's say, build an algorithm to play a certain game. Right? That, for example, was very much a popular thing recently, where you're given an online game like Dota or whatever, and you want to build a bot that plays the game hopefully much better than a human. Or even games like, I mean, physical games like chess or Go. All of these are, I mean, you can't really classify them as one of the types above, because in some sense, in this case, the in most of these cases, you're given something and you output something. The algorithm gets an input and it immediately gives an output and you're done. Whereas in these kinds of problems, the algorithm is essentially interacting with the environment, which is changing. So for instance, if you're playing a game, let's say a game of chess, let's say an algorithm is playing against a human, the algorithm outputs something, which is maybe the next move, and the player plays something, and depending on what has happened in the environment, what kind of external influence is present, the algorithm next takes this into account and then say plays the next move. All right. Similarly, you may also want to design an algorithm for navigating a car through, let's say, a busy street. Right. So these are all cases where there is external influence. The algorithm has to continuously interact with the environment and then make decisions. There's also image or video or text synthesis. Right? Let's say you just give a text prompt and you want the algorithm to output an image corresponding to that particular prompt. Or maybe a video, you want to just generate new video of some particular sort. So all of these are, like, broadly speaking, the kind of problems that fall under the framework of machine learning. Again, it's not an exhaustive list. This is just representative. So these are, like, very broad in some sense, but again, these are engineering problems. The first step to solve any engineering problem is to formalize exactly what is the underlying mathematical or otherwise problem that is involved in each of these cases? Can we completely abstract it out, right? And one way of abstraction is the following: you just classify them into certain types of learning tasks. And these are some learning tasks. Again, it's not an exhaustive list. One problem is that of classification, wherein let's say you're given an image, you want to classify whether this image has a car or not, or you're given spam, you're given, let's say, an email and you want to classify it as spam or not spam. Yeah, so essentially in each of these cases you have some kind of an input, and the output is, say, one of finitely many things. Either it's yes or no, or it's one of these 5 classes. Classification, as the word suggests. And then you also have regression, which is, again, you're given some sort of an input, and the goal is to produce, the output is some sort of a real number or a vector. So for instance, you want to predict the temperature tomorrow. You're given all of the, let's say, weather patterns and all kinds of data, and the goal is to say, okay, what will be the average temperature or minimum temperature tomorrow? That corresponds to a problem of regression. Or let's say you want to design an algorithm to beat the stock market. You want to predict what will be the average value of this stock tomorrow. That's a regression problem. But then, I mean, all of this, it depends on how you formulate your problem. Compared to the previous case where these are like very high level engineering problems, these problems can be formally stated. There's a precise definition for what is a classification problem and what is a regression problem. Now, your engineering problem could be anything. For example, let's take the example of predicting the stock market. You want to decide whether you want to buy a particular stock or not. Correct? Now, there are different ways of viewing this. One is you may want to predict what is the value of this particular stock tomorrow, which makes it a regression problem. But then you could also say, I just want to know whether I should buy the stock or not, in which case it becomes a classification problem. So that is why there is, depending on what your actual engineering problem is, it's up to you to formulate it more precisely. Correct? But once you do that, then you can use all of these algorithms and tools and all this formal framework in order to solve that particular problem. The first step in any engineering problem is precisely formulating what exactly you want to solve. Right. So these are two sort of typical learning tasks, and these are essentially the kind of learning tasks that we will look at in this particular course. But there are many other tasks. For example, ranking. You are given a bunch of items and you have to rank them in order of, let's say, ascending or descending order, which is the best, which is the worst. Or it could be a problem of clustering where you're given, let's say, a bunch of images. You don't know, you're not given any information about what kind of images they are, but you want to group similar images together. Maybe, for example, you're given a bunch of pictures that you click with your phone, and you want to split them into different albums perhaps, and you want to do this automatically. So that can be viewed as a clustering problem. That can be posed as a clustering problem. And then there's this problem of dimensionality reduction or manifold learning, wherein although you have this data or samples flying in a very high dimensional space, for instance, you could think of images which, let's say, have 1 million different parameters, 1 million different pixels. Each pixel can take one of maybe 256 different values, 256 into 3 different values. But the goal is to, in some sense, compress it, in the sense that you don't want to lose any information loosely speaking, uh, in the sense that you may want to use it for other machine learning tasks, but you want to bring it down from this very high dimensional space to a much smaller dimensional space. Of course, here the underlying assumption is that whatever objects you see actually lie in a very much smaller dimensional space, not necessarily a vector space, but a much smaller dimensional space or a manifold compared to the space in which you observe it. And then there are problems of online or reinforcement learning, so in all of the previous cases, we generally assume that all of the data is available at once, and then you design an algorithm and then you just use it. Whereas in problems of online or reinforcement learning, the algorithm is allowed to improve as and when you see more data. You don't get all of the data at once, but you keep making observations and refine your algorithm as and when it sees more and more observations. Again, this is just a small sampling of the kinds of learning tasks that you may have, and each of these learning tasks can be has a mathematical definition, can be defined mathematically, and you can make statements, can precisely make statements about what can be achieved and what can't be achieved in these cases, of course under certain assumptions. Right. And so in this course, as I mentioned earlier, we'll be looking at sort of a broad class of problems called supervised learning problems, wherein you make some observations, you get some data, and you design an algorithm, and then you go out and test it. You start using it immediately. So once you design the algorithm, that's it. There's no more that can be done. And also this is supervised in a sense that you don't know what the ground truth is, but you're given some data which is labeled in some sense. I'll make all of these precise as we go along, but essentially you observe a bunch of random data, you design an algorithm, and then you use it. That's the broad framework of supervised learning. All right. Any questions so far? Okay. So one other point that I want to make is, what is the difference between, let's say, designing an algorithm for performing some sort of a computation versus designing an algorithm that is expected to learn? What do you think the fundamental difference is? So for example, you want to design an algorithm that can compute the Fourier transform efficiently. It's one problem. The other problem is you want to classify whether a particular piece of text is spam or not. When you actually want the algorithm, you keep updating. What do you mean by the parameters? Okay. We have to increase like x of e to the power minus j that we have to do. Like suppose we have to like classify something like suppose we just have to suppose we have a matrix and then we keep updating it again and again depending on the count in the right. Okay. I think you're kind of hinting at it, but any other answers? By a set of correct. And as the data comes in, whatever data input data is supplied, right to it's correct. So the objective is already fixed in terms of one. Yes, it's sort of correct. But one main difference between learning and computation is that the underlying model, the ground truth, is unknown. That's the fundamental assumption here, right? There is some underlying model, but you don't know what that underlying model is. You're only given data in some sense, and your goal is to design an algorithm purely based on this data. And this data is to be a representative of what the underlying model is.
It is also a deterministic, right? Because in one case we are solving a specific task where we are giving some input data, like if you consider task of solving sorting, we are giving an array and we are sorting it off. That is the one class of algorithm. And when we are dealing with here, we are getting the input as a training data, and the output is a classifier which separates this training data. And the process in which get the output as a classifier is an algorithm. That is also a deterministic. It returns the minimum classifier with minimum what is our objective.
So the algorithm may be deterministic or random, right? Even for a computation problem. For example, suppose you want to design an algorithm which tells you whether a given number is prime or not. Now you can construct a deterministic algorithm for this, but you can also construct a randomized algorithm which gives you, let's say, there is some source of randomness, some additional randomness that this uses, and it gives you maybe the correct answer with some probability and gives you the wrong answer with a different probability, with 1 minus that probability. Right? That's not the point here. So even for a problem of computation, let's say even sorting, you could cook up a randomized algorithm to do sorting. There's nothing wrong with that. But then the underlying problem, in the sense that the underlying model is known to you. You're given, you know that you're going to see a bunch of numbers, okay? And again, you make some assumptions, of course, and the goal is to sort it. You know exactly what you need to do. But the problem in learning is that you don't know what the underlying model is. So you only interact with the model through data. You're only given a bunch of samples.
According to our
Correct. But also the algorithm can, like, depending on what data that you observe. So the point is that the algorithm that you design is in some sense dependent on the data that you observe, right? Which is not the case in, let's say, okay, so let's take the problem of spam classification. Right? You observe some emails. So how do you design a spam classifier? One way is to, let's say, take a bunch of emails which have been already classified as spam or not spam, and you design an algorithm to basically get a spam classifier. All right. Now, depending on what data that you see, it's not so you of course, if you are allowed to see all of the possible emails in the universe, then you could design a spam classifier, a perfect spam classifier. But that's not what you have. What you have is some limited data, so some representative data, and using that you have to design a spam classifier. And that is what distinguishes learning from computation. Whatever algorithm that you design also depends on what data you see, which is not the case, for instance, when you're designing an algorithm to compute the Fourier transform or designing a sorting algorithm. Correct? In this case, let's say you fix how you are going to learn. Once the learner is fixed, you decide to choose an algorithm based on a certain rule. Now this rule depends on what data you see. Correct? If you get good data, maybe that's great, you perform well. But if the data was bad, then even though you're trying to do the best, you could still do badly in the real world. So your interaction with the model is with the data. And how well you perform does not only depend on how well you designed your learning scheme, but also depends on how well your data approximates reality. That's why it's learning. Any other questions? Okay. So let's get down to it. Let's try to formally define the learning task. Okay. So in supervised learning, you're always given what I call labeled data. And the labeled data consists of two parts. One is, so for instance, in the example of spam classification, you are given two things. One is the text itself, maybe it's a piece of email, and the other is a label which says whether it is spam or not spam. So that's what I mean by examples or instances. So this could be the email text, or if, let's say, an audio clip, maybe you're trying to find the genre of a particular song. You're trying to design an algorithm which, given a particular song, tells you what genre it belongs to. And you're also given the data, the corresponding labels for each of these instances or each of these examples. So this could be a label whether it is spam or not spam. For example, if you have an audio clip, there's also a label saying whether it is rock or pop or something. Right? So, and in supervised learning, again, the framework is the following. You're given a bunch of labeled data. Right? So let me call the examples, denote the example as using X. That's, I'll also introducing notation at this point. So examples or instances will typically be denoted by X, and the corresponding labels will be typically denoted Y. So you're given essentially what I call training data. So essentially you have n examples or instances and the corresponding labels. Right? So this is what is given to you, and from this training data you have to design an algorithm which will perform well, not just on this training data, that would just be a problem of computation, but the goal is to perform well on some new data that you've never seen before. So from this data, you have to design an algorithm which will predict whether a given piece of text is spam or not spam, or find what is the genre of a new audio clip. All right, so it's a kind of a two-step or three-step process. And once you complete a stage, you don't go back. Okay, so and the main point is this data is labeled data. That's the assumption in supervised learning. And this is the framework that we will follow. So everything is done in one shot. You get all of the data in one shot. You design the algorithm, and then you're done. There are other variants, other kinds of problems. For example, in a problem of unsupervised learning, you only get the examples or instances themselves, and you don't see the labels at all. So for instance, if you're doing clustering, you know that there are data corresponding to different, let's say, topics. Now, obviously, you can't predict what the topic is because you were never told what it was. But then you could say that, okay, these particular objects correspond to the same topic. So, for instance, suppose you go to, you've just learned to read, but you don't know different concepts. You don't know what is mathematics, you don't know what is physics, you don't know what is biology. But you get to see a whole bunch of books. You don't know that they're called biology books or physics books or mathematics books. But then if you read a bunch of books, you can say that, okay, these two books are similar to each other. Right? If you take two different physics books by different physics authors, you could say, okay, these two books are similar to each other compared to, let's say, a book on biology. So you can classify them even if you didn't know that they're called physics books or called mathematics books or biology books. So that's an example of unsupervised learning. And you could also have so-called semi-supervised learning problems. You're given, let's say, a few books. Suppose you're told that, okay, this is a physics book, this is a mathematics book, this is a biology book. You're just given one book. And you're given a bunch of other books. But you're not told whether these books are physics, mathematics, or biology books. But based on similarity, you can say that, okay, now I have three books, one physics, one mathematics, and one biology. And okay, these books look similar to the physics book, so let me just classify them as the physics book. These books look similar to the biology book, so let me all classify all of them as biology, and this one as mathematics. The point is, this distinction may or may not be clear. For example, there could be books that have both math and physics topics in them. Or maybe it's a book on computational biology which has some math as well as some biology. So now deciding whether it is a biology book or a math book, it may not be so clear. But in this course, we'll assume that the data that you have is fully labeled. Right? The training set or the training data that you're given is so for each example or instances, you know what the correct label is. You want to design an algorithm which will do well in the real world. Even if you observe something which is not in your training set, it still has to do well. But of course, before we get to that, we have to first understand what does it mean to do well, right? And what kind of an algorithm are we allowed to design? How should we go about designing an algorithm? And how do you put all of this in a mathematical framework? Now, no matter what you do, you have to make certain assumptions. For instance, you have to assume that the training data that you get is in some sense representative of the real world. Otherwise, it makes no sense. You can see that it's impossible to design a learning algorithm. And similarly, you have to also assume that the training data, of course, it's representative, so there's enough diversity, so to speak. But it also has to be, in some sense, consistent with what you will see in the real world. I'll make this a little more precise. But of course, we have to make some assumptions. But at the same time, there's no point in making too many assumptions. The goal is to make the minimal set of assumptions that will allow you to study this in a formal framework. Right? So, okay, let's start by introducing some more notation to make things more precise. As I said, we'll mainly be focusing on the supervised learning problem, where there are examples or instances and their corresponding labels. The goal is to predict the label given a new instance. So firstly, before we even think about what the ground truth is supposed to be, we of course need to identify what are these objects, the examples, instances, and labels. So the domain set, let me denote this by script X. This is essentially the set of all possible examples or instances. Right? So for instance, if we are dealing with, say, email classification, then the instances are basically emails, right, which are paragraphs of text. So X would be all possible text in the universe, maybe with a word limit. So basically, it consists of a bunch of characters, which have at least one character and maybe a maximum of, I don't know, certain number of characters, perhaps. In the case of, let's say, song classification, maybe the domain set is the set of all audio files of a certain duration, maybe. Or maybe a more mathematical way to think of this is set of all signals or set of all functions from or set of all functions that operate on a certain interval. So each x could be a set of functions f of t, 0 less than or equal to t less than or equal to the duration of the song. Again, you could have some more information. Maybe f is not set of all possible functions, because it has to correspond to audio, so maybe it is band limited and so on. Again, the point, I'm trying to introduce some subtle points over here. In general, you may not know exactly what the domain set is. For example, let's look at all possible songs. Which one? This one? So the way I've written it over here, it's a set of all functions that operate on the interval from 0 to t. So all possible audio files or all possible audio of duration equal to capital T. In the context of song classification only. But again, this may be too rich a space, because not all of these functions correspond to valid songs. Right? So the class of all possible songs is potentially smaller than this, much smaller than this. But we still, in certain cases, it doesn't matter. We won't care what the actual domain set is, but it's large enough. Okay. Now, each of these instances have an associated label. and the label set will be denoted Y, capital Y. So in the context of email classification, this Y could be just spam or not spam, or you could also map this to 0 or 1, where 0 means that it is spam and 1 means it is not spam. Again, in the context of songs, Y could be the class of all genres. Rock or pop or something else, classical, and so on. But again, without loss of generality, I can assume that it is just 1, 2, 3 up to M, where M is the number of classes. Okay. Now, so we'll make certain assumptions right at this point. So the label set Y without loss of generality, we'll either assume that it is the set of real numbers, or it is in the case where we are trying to classify into finitely many classes, we'll just assume that it is 1, 2, 3 up to M, where M is the number of classes. How you label them is irrelevant, just that there are M classes, whatever they're called. All right. And the domain set is any arbitrary set. We will not make any assumptions on that. Okay. Okay, so we know what the input is going to be. We know what the output has to be. But how is the data actually going to be generated? Now, now is the point where we'll have to make certain assumptions. So essentially, what is the ground truth? So one way of determining what the ground truth is, let's again take the class or take the problem of maybe classifying images or classifying spam. Okay, classifying emails into spam. What is the domain? Set of all possible images, or the set of all possible texts, all possible emails in the universe. Now, if you are given in this very specific example, if you are given the image or you are given the text, it's either spam or it's not spam. It's either it has this particular object or it doesn't have an object. So you can, it's sort of a yes or no question, and the rule from the image to the class is deterministic. Right? So that's you can assume that that's the ground truth. Right? So in other words, you could assume that the output is equal to some function, or the label is always equal to some function of the instance, some deterministic function, which of course you don't know. Correct. So it is the label, I agree. But the question is, from the instance, how do you get the label? And right now I'm saying that the label is a deterministic function of the instance. In the case of, let's say, spam classification, maybe it's clear whether this is given a piece of text, you know it is spam, you know it is not spam. So this is sort of a deterministic model for the ground truth, but of course we don't know what this function is. So effectively, if you want to search for a good learning algorithm, one way is you look at all possible functions from all possible deterministic functions, from the instance, from the domain set to the label set, and you choose the best. And if you're able to somehow magically choose the best, then you're done. Right? The problem is you're not able to do that. So this function C is sometimes called a concept. All right, and the space of all, maybe now C could be any arbitrary function from the domain to the set of labels. Okay, but that's not necessarily true. In general, maybe you know something about the relationship between the label and the instances. So you could instead, maybe you know that C comes from some restricted class of functions. And that class of functions is called a concept class. So C is a map from the domain set to the label set, and we will assume that C comes from some set of functions, and this set of functions is called a concept class. Right? So this is some information that you will need to know about the ground truth. Which one? Y is given to you, yes. So there are two different things, right? One is the set itself, right? Script Y is the set of all labels, right? Which is, in the case of spam classification, it is spam or not spam. So it's a set of size 2, right? The label is different from the label set. So when I say label set, what are all the possible labels? So in the case of emails, for every instance, which is any arbitrary text, it can be either spam or not spam.
Element in the domain set, given the label by spam or not.
Yes, and okay, yeah, for now, yes.
So then when we are saying this label y is equal to C into x.
Y is C of x. It's some function of x.
So this y, that y is called as label, this y is called as ground.
So okay, so again a little bit of, maybe it's a problem with my handwriting. Let me go back. Let me denote the label set by something else. Maybe something like boldface Y or something. This is going to be my label set. Little y, or this y, is the label. Yes.
And this is label
C of some x. So C is a function.
This y, little y is also called as ground. There is no difference.
No. So let's do it step by step. So right. So C is a function from the domain set to the label set. Okay. The question is, how do you represent the ground truth? How do you mathematically represent the ground truth? So the label is essentially, for each x there is a label. Right? It's a variable, so to speak. The ground truth, I'm trying to represent the ground truth using a function, which the function for each instance outputs a label. So you think of the ground truth as a black box. All right, the black box takes as input an instance and outputs a label. Okay, and how is the output? How is the label? So this is unknown to us, right? There is some black box. Okay, and your goal is to somehow try to approximate. The goal of supervised learning can be thought of as trying to approximate what this black box does. You're trying to imitate what this black box does as well as possible.
This black box is the ideal black box.
This is the ideal black box.
It's basically when we have all image entire universe.
Yes.
Then
It's always going to output the correct answer.
this is what the black box.
This is the, yes?
This is why I have predicted.
There's no prediction yet. There's no prediction yet. This is what I'm trying to represent as the ground truth. This is a black box which we don't know C. The goal is, in some sense, to approximate C. The whole main goal of supervised learning is to be able to approximate C.
It's basically the true relation.
Exactly. So C is the true relation between the input and the output. So, correct. Well, okay. Y is the true label for X. Okay. So you can think of label as a variable. Correct. Again, it will become a little more clear as to why I distinguish between the label and the ground truth. For now, I'm saying that the ground truth is a deterministic function, or basically the ground truth is the relationship between the instance and the label. The true relationship between the instance and the label is what I call the ground truth. Right now I'm saying it's a function, okay, which may be more reasonable to expect in this example of, let's say, classification or text classification. Right. So in this case, this ground truth is represented by a function, the actual relationship between X and Y, and this function is the true function is going to be called a concept, and we assume that this concept comes from some class of functions. Maybe that's called the concept class. Now the concept class could be the set of all possible functions from X to Y, but not necessarily always. It could come from some subset of these functions. Again, that's why, since we're trying to put it down mathematically, maybe you already know, for whatever reason, maybe for physical reasons, that C cannot be any arbitrary function, but it has to be from some specific subset of functions. Maybe it has to be smooth, right? Because of whatever, maybe it comes because of physical reasons.
We will take curly X.
So curly X is whatever, it's a domain set.
So you know about this curly X is collection of all names.
So first, this is the domain set, right, which is where your instances come from. So curly X could be the set of all possible images, right? But C is the set of all functions from all possible images to the label set. That's one way. What I'm trying to emphasize here, it is one way of modeling the ground truth or the data generation model. There is some underlying true function between from the domain set to the label set, and the goal is to learn this function, so to speak. But again, that's only one way of modeling this. So, and this happens in the case where, in some sense, you have all the information that you need to determine what the label should be. But there are a bunch of problems where you don't have all the information that you need. There could be other influencing factors, so that for a given X, this relationship need not be a direct functional relationship. So, for example, suppose the goal is to find out whether a particular apple is going to be sweet or not. Okay? Now, for this problem, what one needs to decide what the domain set is going to be. It could be the collection of all apples, but maybe you're not told that. You can't give that to the algorithm, right? You can't give the apple to the algorithm. So what do? Maybe you make some measurements and you give this to the algorithm. Maybe you say that what kind of measurements can you make? Maybe you can measure the size of the apple, maybe the diameter and the height. Maybe you can measure find out the color of the apple, the weight of the apple, and so on. So you measure a bunch of these parameters and then you feed it to the algorithm, and the algorithm is supposed to predict whether this apple is going to be sweet or not. Now in this case, again, it's not, maybe you don't have, in this case, you don't have the full information, right? There could be two apples which have the same set of measurements, but one of them could be sweet, the other is not sweet. So in some sense, you're not able to observe everything you need to observe in order to say whether it belongs to this class or not, or that class. So there is some other source of randomness that you're not able to observe. Correct? That is, in your training set, you're somehow able to tell whether it is what the correct label is. So for example, in this case of determining whether an apple is good or not, what do? Well, you make some measurements, maybe the dimensions of the apple and the weight of the apple and maybe the color. You list all of these out, and then you can take a bite of each apple, right? So you know whether it is sweet or not. You can make that measurement and decide and find out what the true label is. Okay? But now, what is the goal of the learning task? You're given you now have to design an algorithm such that if I give you a new apple, without eating it, can you predict whether it is sweet or not? Right? That's the learning task. Right? So in the second case, you don't know, there's no functional relationship between the input and the output. In fact, the relationship is random. So we assume that X and Y, I mean, even here, it's a little bit incomplete. I've not told you everything that I need to tell you, but the assumption is that given X comma Y, this is distributed according to some unknown distribution Pxy. Okay. Again, all of these are unknown. So even in this case, where the relationship between the input and the output is fully deterministic, there could potentially be a source of randomness, and that is in X. All right, because maybe it's possible that certain kinds of inputs are more likely. For example, suppose you're trying to design an email classifier. Now, we made certain assumptions on what the domain is, right? Which could be the set of all strings from a certain alphabet. Let's say all possible English strings, basically strings from the English alphabet and special characters. Now, some of these correspond to valid text, but some of it could be like complete garbage, which is something that you will not see in typical emails. So the inputs are also come from some specific distribution, so to speak. And that all of that is modeled by this distribution Px, which is again unknown. Okay. So no matter what we do, there is always some source of randomness in the system, and that is going to be a fundamental assumption. And even in this case, when the relationship is not really a concept, the relationship could potentially be random. So in some sense, this randomness is takes into account the information that you don't have, some missing information.
If there is a randomness in X, then there is a randomness in Y also.
Correct. But given a particular X, is there still more randomness in Y? So for a given X, right? So I agree that if X is random, then Y is random. But conditioned on X, is Y random or not? Not always, right? In this case, X is random, but conditioned on X, Y is determined, right? In the first scenario. In the more general scenario, even for a given X, there could be some other source of randomness for which now Y is still not fully determined. So if you go back to our example of determining whether an apple is good or not, there's some more randomness. So even though you have the same dimensions, with certain probability you can say that whether it's good or not, or with certain probability it is going to be good or not. The only source is in Px, right? It could be anything. There's no assumption on Px at all.
Environment is affecting the label side. If they are getting one domain value that it being influenced by the environment, they are seeing another domain.
Correct. That's one way to think about it. Or even if you think of, let us say, valid images. Or maybe, yeah, you want to think of designing a spam classifier. Now, it's not completely arbitrary text that you get, right? It's not random strings that you observe. Most of the emails that you get will have a certain structure to them. Whether they're spam or whether they're not spam, they still will have a certain structure to them. All right? And all of those external influences, who is writing the email and so on and so forth, all of that is captured by this Px. Okay. Any questions? All right, so that sort of sets up what the ground truth or the data generation model is. So this is representative of the ground truth. Now, as I said, in supervised learning, you get some training data. And the assumption in supervised learning is that you observe n samples, that is n instances along with their labels. And the goal is to design an algorithm such that given a new sample, a completely fresh sample, you are able to predict the correct label reasonably well. Okay, so again, assume that what was the ground truth? The ground truth is that x comma y is drawn from a certain distribution in the more general case, but it could also be that the relationship between x and y is deterministic, and essentially C comes from some concept class, right? But the underlying assumption is that when you observe a new sample, it is going to be distributed according to Px or Pxy. Right? And if we are to design a good learning algorithm, then the training data has to be representative of the ground truth. Otherwise, there is no hope. So in particular, we'll assume that these xi, yi's, these are also distributed according to the ground truth. Okay, so the fundamental assumption is that xi, each xi comma yi is distributed according to Pxy in the general case, and if the true relationship comes from a concept class, then yi we always observe xi comma yi equal to c of x. Right? So that's one assumption. So it's representative of the ground truth. The other assumption is that this data is diverse enough, in the sense that we'll assume that these xi, yi's are all independent and identically distributed. Right? They have to be independent, otherwise you're not getting enough information about the ground truth. Correct.
That means itself implies that they are identical.
They're identical. Yeah, it only implies that they're identical. But then, I also want them to, the samples to be independent of each other. For example, let's consider a almost nonsensical scenario where I just draw one sample and I repeat the same sample 100 times. Now I have a data set, I have a huge data set, but it doesn't represent the ground truth well enough. I'm not getting much information out of this. I have 100 samples, but they're all equal to each other because they were all drawn, of course, identically distributed. It is distributed according to the ground truth, but they're not independent. Correct? That's also, I mean, it's an important notion. For instance, let's say you're trying to design a machine learning algorithm, and say you're given some data. Now, what some people can try to do is, from this data, you try to generate new data. Right? From your training set, you have a very small training set. You try to generate a much bigger training set by whatever, making some modifications on this training set to try to get new samples. Now, if you try to do that, then potentially you can run into the problem that these are not independent of each other. Maybe they're all identically distributed according to the ground truth, but they're not independent enough. So in fact, the amount of information that you're getting about the ground truth is actually much less than what you really need. And your learning algorithm could totally fail when you are presented a completely new sample.
The second is the ground truth in OX.
I'm sorry?
PXY is the ground.
Pxy is the ground truth, yes.
So we have made the assumption that all of the x's.
Correct.
What will happen if they're not?
If they're not IID, then many of the results, basically many of the results that we are going to show are will not hold. Why do you need them to be independent, you mean? If they're not independent, then again, intuitively speaking. So right now we're making assumptions, and we need to make some assumptions in order to proceed, right? Again, what is the minimal set of realistic assumptions that we can make such that everything still goes through? Now, of course, it's a natural question to ask, and you may want to, in fact, relax some of these assumptions. Going back to the example I just mentioned, maybe you actually have very limited data, but somehow you're trying to generate new data, maybe through some other source of randomness, somehow. Try to enlarge your data set by generating new points from that data set, that smaller data set that you had. Now it's no longer independent and identically distributed, but you still want to know how well you can learn. That's a natural question to ask. But that in general is harder to answer. Unless, of course, there could be some structure, in which case you could say some more things. But in general, we need to know something about the way the training data is generated. And the way that we will model it is that it is independent and identically distributed. So in fact, you see that some of the, even if it is not IID, let's assume that it's drawn according to a Markov distribution or something, many of these results will still carry forward. But of course, in making those assumptions, you are in fact increasing the number of assumptions that you have. Because right now, what did we have? The only assumption about the ground truth itself is that it's according to Pxy. There's nothing else. But if, let's say, you say it's going to be generated according to a Markov process, then Pxy is not sufficient to describe your training data. You also need to know how is Pxiyi dependent on Pxi minus 1 yi minus 1, where in fact you're imposing more assumptions. The goal is to always build a framework using the minimal set of assumptions. And that's called Occam's razor. Occam's razor. Right? Basically, loosely speaking, it says that the minimal set of assumptions is always the best. The simplest set of assumptions that describes the ground truth is always the best to choose. Okay, so essentially, what is the framework? Now, as I said, you're given labeled data, and that is training data. The goal is to design an algorithm to learn from this particular data. But what do you do in practice? So the goal is to always ensure that your algorithm will perform well out there in the real world. So given this training data on a completely new unobserved sample or an unobserved instance, your algorithm has to do well. But how do you know whether an algorithm is going to do well on an unobserved sample without observing it? That's hard to say. And that is why the fundamentally, how do you say whether a particular learning algorithm does well? You take your labeled data and you split it into typically 2 or 3 parts. The training data, what is called the validation data, and it should be test data. So you use your training data to design an algorithm. Now, in general, you may have some extra information about the problem itself. And maybe from the training data, you extract certain features. You know that only these features are relevant to you somehow. This is whatever, some side information that you may have. And then you design your algorithm, or through this process, which is called the process of designing the algorithm, is what we'll call training. All right. But at the same time, you may have certain extra parameters in your learning algorithm. Sometimes these are called hyperparameters, and you're not sure which set of hyperparameters to choose. So for example, suppose you're trying to train a neural network, or maybe your algorithm is in the form of a polynomial, and you want to decide what is the correct degree of the polynomial you want to use. So you could think of the degree as a so-called hyperparameter. So what one can do is, okay, you choose a particular degree, you train, see how it performs, take another degree, again train, see how well it performs. Now, how do you decide between these two degrees? You use this so-called validation data, right? So you use this to choose hyperparameters. Now, again, in this course, we won't really worry about hyperparameters or validation. We'll somehow assume that all of this essentially comes under training. You have a bunch of training data, a bunch of labeled samples, and then you design an algorithm through whatever principle, and then it outputs some function. But now you need to know how well this is going to perform on unseen data. And one way to test this empirically is to test this on other samples which have not been used in the training data at all. And that is called test data. Now, again, the intuition behind this is that if you have enough test data, now again, this test data is the one fundamental rule that you have to remember is that your test data should not be used to design your algorithm or make any tweaks to your algorithm. That should always be untouched. Right? The test data is something that you finally use in order to see how well it is going to perform over an unseen sample. Basically, once you design an algorithm and once you use the test data to see how well it performs, you're not allowed to go back and then tweak something in the algorithm so that it does better in the test data. That doesn't work. That's essentially cheating. Right? So if you have enough test data, then it is reasonable to expect that the empirical performance on this test data would closely approximate the average sample over a random instance. And that's the basic principle behind empirical testing. We'll see that in a couple of examples later. All right. Okay. And maybe one last thing before we end this class. Okay, so this completely describes the data generation process and the training set. What is a learning algorithm? A learning algorithm is essentially going to be a function from X to Y. Right? So the goal of the learner is to output a function H, which outputs a label for every instance. Output H that does well on a new sample or a new instance. Now, can H be completely arbitrary? Maybe not. Maybe you want to restrict the choice of functions H that you can choose. And this H is assumed to come from some set, some class of functions, which we call the hypothesis class. So each H is called a hypothesis. And yeah, so now Up to this point, we've kind of formally defined everything. Kind of, we've defined what the domain set is going to be. The label set is the ground truth. It's again drawn according to some distribution pxy, which is again unknown, but it's fixed. There is something which is fixed but unknown. And the training data is going to be independent and identically distributed. So we've all fixed that. The last thing is to decide how do you output, how do you say whether a particular prediction is good or not. We'll explore this in the next class. So let's stop here.